The next item on the agenda is a presentation by CNSC staff on counterfeit, fraudulent, and suspect items as outlined in CMD 14M3. And I understand that Ms. April Masses will make the presentation. Please proceed.
Thank you. Good morning, Mr. President and members of the Commission. My name is Kathleen Masses. I am the Director General of the Directorate of Safety Management in the Technical Support Branch of the CNSC. With me today from our Directorate are Mr. Pierre Lahaye, Director of the Management System Division, and Mr. Paul Wong, who is a Management System Specialist. Monsieur Jerry Frappier, the Director General of the Directorate of Assessment and Analysis, and members of his teams are also with us to offer technical support in the areas of fitness for service and defense in depth. As well, I understand that we have some members of the industry that are here with us today. Mr. Terry Davies from Point Le Pro, and I believe Mr. Frank Saunders from Bruce Powers are here with us today. They can answer further questions. The purpose of today's presentation is to provide you with a briefing on the topic of counterfeit, fraudulent, and suspect items, more commonly referred to as CFSI. This subject surfaced in other countries in the last few years, and we thought it'd be useful to make a presentation on that subject. Product counterfeiting is not a new phenomenon. It has been going on since the dawn of commercial trade. To give this some perspective, counterfeiting of coinage dates back to ancient times, and the earliest record of art forgery dates back to 1524. Today, numerous consumer products are subject to counterfeiting. Bringing this back to today's nuclear industry, recent international reporting of instances of CFSI has underscored not only the importance of detection and control provided by robust supply management processes, but also the defense of systems, structures, and components as they relate to defense in depth. I will now turn to the outline of today's presentation. Our presentation will start with a brief background about CFSI in general, and will include some illustrations of the different types of CFSI. We will then describe the factors that are contributing to the threat of counterfeit and fraudulent items into the supply chain. Some examples of CFSI reported internationally will be provided, and the actions taken by the international community to address this threat. We will talk about the measures we have in place in the Canadian regulatory framework to address counterfeit and fraudulent items and the actions the industry has taken. An explanation of the various layers of defense we currently have against CFSI will be given. We'll end with a description of the initiatives we are taking to further address counterfeit and fraudulent items. What are counterfeit, fraudulent, and suspect items? The definitions you see on the slides are those adopted by the Nuclear Energy Agency, NEA. Counterfeit items are defined as items that are intentionally manufactured or altered to imitate a legitimate product without the legal rights to do so. For example, items would not be made of the appropriate material, labels or tags might have been altered, or casting marks might have been ground off and stamped with other markings. Fraudulent items are defined as those items that are intentionally misrepresented to be something they are not, whose material performance or characteristics are knowingly misrepresented. For example, items can have incorrect identification and falsify or inaccurate certification, including testing certification. Suspect items are defined as items where there is a suspicion that the item may be counterfeit or fraudulent. There would be an indication by visual inspection or testing that they may not conform to the accepted standards, specifications, or technical requirements. When we talk about CFSI in this presentation, we will be discussing items where there is an intent to deceive. This does not include items that are not conforming due to design or production defects, damage during shipping, handling, or storage, and improper installation. Let's look at a few generic illustrations of counterfeit items gathered from literature for the purpose of demonstrating the types of CFSI that can be encountered. On this slide, we can see differences in the paint color and the markings on the body of the two valves. It would not be immediately evident which one is the counterfeit item. In this case, the marking on the counterfeit valve was added by grinding and welding, whereas that of the proper valve was casted into the body. For the circuit board, the counterfeit board has on the right a button in the wrong location and is physically thinner than the genuine circuit board. On this next slide, we're looking at the product labels of circuit breakers. The labels for the genuine and counterfeit breakers look very different, and on the surface, it is difficult to tell which would be counterfeit. The counterfeit breaker label is missing many of the features of the genuine item, such as the word listed in capital letters and a sequence of alphanumeric characters. Moving on to an illustration of a fraudulent item. It is a case of documentation containing false information about the material being supplied. The document certified non-nuclear grade steel as nuclear grade steel. These fraudulent documents were supplied by a foreign company on a U.S. company's letterhead. So those were a few examples. Let us now look at the factors that are contributing to instances of counterfeit and fraudulent items worldwide. Let's discuss those 4 factors. First, there have been changes to the nuclear supply chain over time, such as a more globalized economy, the relocation of manufacturing centers offshore, the arrival of internet-based suppliers, and an overall increased length and complexity of the supply chain. Second, there is an increased difficulty in procuring replacement parts. The original manufacturer may no longer be making the part. There is a smaller and smaller pool of manufacturers undertaking the stringent demands for the rigorous testing and documentation needed for some nuclear-grade items. A third factor contributing to the increase in potential CFSI cases is the increased demand of nuclear components. The increased demand is caused by a number of sources, including, for example, aging and obsolescence of existing equipment and new build projects. Some of the modern electronics used in digital instrumentation and control technology tend to have a shorter life cycle compared to the traditional analog components. This, in turn, increases the frequency that these components need to be replaced. The final factor that we'll discuss is the challenge in detecting counterfeit and fraudulent items. Traditional procurement programs were designed to identify and manage non-conforming parts and services. The criteria used to confirm the quality of products during receipt inspection and testing generally assumed vendors' integrity, and the criteria were not focused on identifying an intent to deceive. As a result, these programs were not originally designed to detect counterfeit and fraudulent items, since additional measures have been put in place to do this. With modern off-the-shelf technology, it has become easier to replicate traditional manufacturing processes, allowing for the ease of counterfeit production that resembles the genuine products. CFSIs that are embedded in a black box would also present another challenges for detection. We'll now take a look at some of the cases reported, of CFSI reported worldwide. There were a number of CFSI cases in the US in the late 1980s and early 1990s. More recently, there have been reported cases of CFSI in the US with electrical equipment and valves, just as the equipment that we looked at in the earlier slides. A CFSI case was reported in Japan where the test data was falsified. In response to a survey by the Nuclear Energy Agency in 2011, The other countries listed on this slide reported that they have not detected cases of CFSI. The recent CFSI cases in Korea have been widely reported in the media. In September 2012, Korean regulator received an outside tip regarding CFSI. The regulators then conducted a special investigation of all 23 operating units in South Korea. 2 reactors were shut down, while another 2 were allowed to continue operation while the fraudulent parts were being replaced. These fraudulent parts came from 8 separate suppliers who falsified certificates for over 13,000 components. Over 6,000 of these components were installed in the power plants. These were for non-safety related equipment. Later on that year, further investigation uncovered new instances of falsified certificates at 2 other reactors. An additional 1,000 components were affected, which included reactor water cooling system components, pumps and cylinders heads for diesel engines, and raw material for parts. In April 2013, Korean authorities received another outside tip. Upon investigation, the authorities discovered that control cables that had failed a required test were supplied with falsified certificates to 4 reactors. Tests on the cables had been conducted by a Canadian company who documented that the cables had failed. However, the test results were then modified by a Korean company to state that the cables met requirements. The Korean regulators shut down 2 operating reactors and delayed the startup of 2 other reactors. The cables have since been replaced, and the Korean regulators has now given the operators the approval to restart operations. Around the world, the topic of CFSI has generated international interest. International organizations have discussed this topic and have issued various reports. The IAEA, for example, has issued a tech doc providing guidance on CFSI. The Committee on Nuclear Regulatory Activities, CNRA, of the Nuclear Energy Agency has a working group focusing on operating experience. In 2010, this working group identified CFSI as a focus topic. The group sent a survey to all member countries and produced a report in 2011 based on the result of the survey. The CNRA then formed a task group in 2011 to further explore CFSI issues and to identify measures to enhance the integrity of the supply chain. This task force issued a report in February 2013 documenting causal factors of CFSI, the importance of an engaged and informed supply chain, suggestions on actions and control that licensees and suppliers should consider, and recommendations for actions to be taken by regulatory bodies. The CFSI task group recommended to regulators that they enhance their regulations and guidance to explicitly address CFSI, that they define expectations and protocols for handling CFSI, they assess the licensees' CFSI's programs, and share any CFSI information across the industry. The US NRC has taken a very active hands-on approach in dealing with CFSI. As was previously mentioned, during the late 1980s and early 1990s, there were attempts to introduce CFSI into US nuclear facilities. The US NRC and the nuclear power industry performed a major reassessment of the supply chain, and US NRC personnel assisted investigators and law enforcement officials to identify and prosecute the sources of these materials. In addition, the US NRC issued several general communications to the industry providing specific information related to CFSI activity, which led to a reduction in these occurrences in the US for the next decade. In September 2010, the U.S. Office of the Inspector General performed an audit on the U.S. NRC's vendor inspection program. This audit determined that the U.S. NRC's overall approach to CFSI was primarily reactive, and that the agency could strengthen its approach by implementing more proactive elements. It also recommended that a formal agency-wide strategy and plan to monitor and evaluate CFSI should be developed and implemented. In response to the audit report, a task force was created to focus on the key issues: keeping CFSI out of the nuclear supply chain, communicating CFSI, actions that should be taken following the U.S. NRC being notified of a case of a CFSI, and oversight of cybersecurity-related items or components. Based on the results of this task force in October 2011, the U.S. NRC issued their agency-wide approach to CFSI, which details the actions that the U.S. NRC is taking to further address CFSI in the U.S. In addition, the U.S. NRC is in the process of creating a CFSI knowledge management webpage to be the central communication tool for disseminating CFSI information. CNSC staff have reviewed how the Canadian regulatory framework addresses CFSI. The Canadian regulatory framework provides significant layers of defense against the introduction of counterfeit and fraudulent items. First, the management system requirements specified in CSA N286 standard state that licensees must have programs in place to ensure that all procured items and materials meet the technical and regulatory requirements necessary for its use. In addition, the N286 standard has requirements pertaining to controlling non-conformances, ensuring only approved items are used, and also has requirements for the sharing of experience. Next, the CNSC has reporting requirements for safety-related systems that have become degraded, which could have been caused by CFSI. Another layer of defense is provided by the various requirements, which ensures that all systems, structures, and components important to safety are designed with sufficient quality and reliability. Two notable features of these design requirements are the use of redundancy and diversity in the design. Another design requirement is equipment environmental qualification. This qualification ensures that the equipment continues to function under all anticipated environmental conditions to ensure safe shutdown, removal of residual heat, containment, and monitoring. Fitness for service requirements are the next layers of defense. The CNSC regulatory document for reliability programs for nuclear power plants, RDGD 98, requires that the systems important to safety meet their defined design and performance criteria at acceptable levels of reliability throughout the lifetime of the facility. This reliability program is implemented through surveillance testing, inspection and measurement of system structure and components performance or physical characteristics in order to verify their reliability and their state of readiness to perform their functions. These tests and inspections will reduce the impact of counterfeit items that may make it through those other layers of defense. In addition to the overarching management system requirements for all components that are part of the pressure boundary of the power plant, authorized inspection agencies, such as the TSSA, known as Technical Standards and Safety Authority, certify and inspect the equipment. These rigorous inspections reduce the possibility that counterfeit and fraudulent items are introduced into the nuclear-grade pressure boundary components. There are two major initiatives that the nuclear industry is taking to address CFSI. The first initiative that we'll talk about was started by the Electric Power Research Institute, EPRI, an independent nonprofit organization that conducts research and development into the generation, delivery, and use of electricity. EPRI issued a report in 2009 that summarizes insights on techniques being used to address CFSI. It also provides guidance on implementing enhanced controls to reduce the risks of these items being installed in plant systems, and identifies measures that supplier and licensees can implement immediately to reduce their risk of CFSI. EPRI also created a database that U.S. and Canadian members are asked to update to be able to track CFSI cases and to learn from those experiences. Another industry organization that is working to combat CFSI is the Nuclear Procurement Issues Committee, also known as NUPIC. NUPIC was formed in 1989 to evaluate the performance and quality assurance programs of nuclear suppliers to U.S. NPPs. In their audits of nuclear suppliers, NUPIC uses specific criteria to evaluate the supplier's program for the prevention and detection of CFSI. Canadian nuclear power plant licensees are members of both EPRI and NUPIC. Some of the measures adopted by the Canadian NPPs include using audited, qualified, and reputable suppliers, incorporating contractual requirements for suppliers' quality assurance programs for the prevention, detection, and disposition of CFSI, carrying out inspections from the receipt of an item to pre- and post-installation, and to periodic inspection and surveillance testing during operation. They have introduced CFSI awareness programs for their procurement personnel. They receive notifications of CFSI cases through the experience sharing network and take appropriate preventive measures. In turn, they share internal experiences back to the network. NPPs are members of both NUPIC and CANDO Procurement Audit Committee, known as CANPAC. Similar to NUPIC, which we discussed earlier, CANPAC's role is to audit the quality programs of CANDO suppliers to ensure that the nuclear supply chain is robust. In September 2010, CANPAC started auditing each supplier's process for preventing and detecting CFSI. Currently, the CNSC is involved in a number of activities to address CFSI. First, the CNSC participates in the NEA Working Group on Operating Experience and on the NEA CFSI Task Group. CNSC staff actively participated in the development of the reports issued by these groups. The CNSC also participates in the NEA Multinational Design Evaluation Program Vendor Inspection Cooperation Working Group, that is known as MDEP. The CNSC is an observer at the semi-annual CANPAC Steering Committee meetings and at NUPIC meetings in the U.S. The CNSC staff have inspected the material management supply chain programs at each NPP, and also recently started liaising with the US NRC to benchmark strategies and to share information. As we have seen earlier, the existing Canadian regulatory framework contains a number of different requirements that also act as barriers against the introduction of counterfeit and fraudulent items. The first line of defense is to ensure that there are proactive measures implemented to detect and prevent the intrusion of counterfeit, fraudulent, and suspect items. In the unlikely event that the first line of defense is breached and CFSI are installed in the NPP, the inspection and testing prescribed by the Fitness for Service program will form the next line of defense to identify and remove those items from service. In addition to these preventive and detection programs, there are multiple layers of defense by applying conservative design and construction with large safety margins, design redundancy and diversity, and the use of multiple barriers. This defense in depth makes the CANDO design less susceptible to effects of counterfeit items. In summary, the primary defense against safety issues associated to CFSI is the fact that all failures have been accounted for in safety analysis, and the design assures safe operations or shutdown for any failures, whether caused by CFSI or other reason. To address the potential threat of CFSI in Canada as it pertains to the supply chain, CNSC staff plan to take the following actions. Staffs have added specific objectives and criteria and inspection guides to enable the evaluation of licensees program for preventing and detecting CFSI. Staff have engaged with industry on the subject, and it has been very constructive so far. Staff will continue to monitor CFSI initiatives nationally and internationally through participation and observation in CANPAC, NUPIC, and the various NEA groups. Staff also intend to reach out to federal and provincial regulators and agencies overseeing other high reliability industries. And staff have added a specific reporting requirement on CFSI to the new proposed regulatory document on reporting requirements for NPPs, Reg Doc 3.1.1. This Reg Doc is currently undergoing a consultation process. This concludes our presentation. Staff is available to answer questions. Thank you.
Thank you.